Very good morning. A hearty welcome to all of you for the last day of FTP on machine learning. Today's session will be on neural networks and introduction to deep learning. Happy learning.
Hi everyone, good morning and welcome to the fifth session of this series on machine learning. And this is the fifth session and the last session on of this series. And today we'll be talking about very popular algorithm in artificial intelligence called as artificial neural networks. Okay. Before we actually jump into artificial neural networks, I'm sure you would have read about human or animal neural networks, right? So we have something called as a neural network in our body that helps do something. Okay, for example, what it does is it has a lot of pieces called as neurons. Okay, so what these neurons do is whenever you do something, these neurons actually take some kind of an information from there and passes it to the next neuron, and the next neuron does some calculation, passes it to the next neuron, and it goes on and on and on till the information or the calculated information is sent to your brain, where some calculation happens and some action is being taken by the human being. Okay, so you're okay. I think I have told this earlier, but human brains are extremely sophisticated artificial intelligence system. Sorry, not artificial intelligence system, intelligence system. They're exactly like your complicated machine learning or deep learning algorithms. Okay, for example, let's say whenever you touch a hot glass, okay, what happens? You'll immediately withdraw your hand, right? How exactly it works? When you touch, let's say the hot glass, uh, there are some neurons that take that information. Okay, let's say the temperature information. Okay, it takes that information, it passes the information to the next neuron where some calculation happens, and that information is again sent back to another neuron, and it keeps going on and on and on till it reaches your brain. Okay, and as I said, your brain is an extremely complicated machine learning algorithm, where like thousands or millions of different machine learning algorithms are running simultaneously. So whenever you touch that hot glass, that information is sent, and your brain suddenly tries to find some pattern associated with that data. Okay, so historically, when you touched hot glass, your hand got burned. When you touched cold glass, nothing happened, it was all fine, right? So the algorithm knows that, okay, if you touch a hot glass, your hand will get burned. So immediately it predicts that, okay, if you do this, this is going to happen, so withdraw your hand. Okay, that is how you withdraw your hand. And this is how your animal neural networks work. Okay, so scientists thought, computer scientists actually thought, okay, why don't we mimic this using something called as artificial neurons. Okay, that is how artificial neural networks were born. um, in fact, this is not a very new algorithm. Okay, this has been there from probably 1960s or 1970s. There were a lot of research going on in artificial neural networks since 1960s. Okay, but only problem that we used to face earlier was the hardware capabilities. Okay, because artificial neural networks are extremely complex, they need a lot of hardware resources to do all these calculations. And as a result, till recently it was not very popular. Okay, because nobody had extremely sophisticated hardware systems. Okay, but during last few decades, hardware systems have grown exponentially. Like earlier, you used to have a huge supercomputer to run pretty complex algorithm, but now you can do it in your regular laptops also. Okay, because of that, artificial neural networks have gained a lot of momentum, lot of popularity. That is one thing. And second thing is, see, humans, as I said, whenever we touch it, we burn our hand. Basically, I said brain has a lot of machine learning algorithms, right? How do they? How did they? How did they? How did your brain come up with those machine learning models? It has learned all these patterns over the years. Okay, like a lot of data points have gone into training your brain, and as a result your brain is so very well trained to do all these things. Okay, similarly, whenever you build your artificial neural networks, you should make sure that you have a large number of data points. uh, eh, and that is one more reason why it was not very popular till recently, but these days people are generating humongous amount of data. Even a small startup is generating like terabytes of data every day. And as a result, to understand or to build artificial neural network, we have enough amount of data. Okay, uh, so this is how your artificial neural networks are very popular these days. Okay, so now let's look at an artificial neural network, how exactly it looks like, what different parts of artificial neural networks are there, and we'll try to understand each of them separately. Okay, so it's actually called as architecture of our neural networks. Okay, so first thing is we have different layers in our architecture. So the first layer is called as input layer, and the in between layer is called as hidden layer, and the last layer that you see here is called as output layer. And each of these layers are connected with the other one. The input layer is connected to hidden layer is connected to output layer, and so on. Okay, so this is how the architecture of neural network looks like. And these circles that you see here are the neurons. Okay, just like how we have neurons in our human neural networks, right? So artificial neural networks have these artificial neurons. Okay, and each of the neurons in each of the layers is connected to the next all the neurons in the next layer. Okay, for example, in our input layer we have three neurons, and our hidden layer has four neurons. And if you see, the first neuron here is connected to all the four neurons in the next layer, and the second neuron is also connected to all the four neurons in the next layer, and the third one is also connected to all the four neurons in the next layer. Okay, and from hidden layer we have four neurons, and output layer has two neurons, and from four neurons also everything is connected to all the neurons in the next layer. Okay, in this case all these four neurons are connected to both the neurons in the output layer. Okay, uh, okay, one more thing is, why exactly is this layers called input, hidden, and output layers? It's simple, as the name suggests. Input layer is the layer that takes your input values. Okay, uh, input is nothing but your feature values. Hidden layer is it's called as hidden layer because it is hidden from the end user. We'll talk about it little in depth in little later section. But what exactly hidden layer does is all your calculations of your neural network. Okay, and finally, output layer, as the name suggests, gives you the output from each of these neurons. Okay, uh, okay, so how does it work? So you have your data set, with your inputs and outputs, right? So those inputs are fed through these neurons. Okay, and there are these connections which are connected from each of the layers in input layers to hidden layers, and hidden layers to output layers. This is a unidirectional move, which means your information is flowing from this to this and this to this. Okay, so input layer is where all your feature values are passed. Okay, and these weights will have some kind of a these connections will have some kind of a weight associated with that, which actually helps determine how much information is being flown from here to the next neuron. Okay, so what happens is this information is flown from here, your input features, and these weights will tell you how much of information should flow to the next layer. In the next layer, some calculations happen. We'll talk about those calculations also in more detail. And whatever calculation outputs that you get will be again flown to the next layer, that is your output layer. Okay, where you get your output, and that is how your artificial neural network works. Okay, and okay, why is this layer called as hidden layer? Okay, by the way, hidden layer, in this case I've just shown one single hidden layer, and that is why it is hidden layer. But you can also have a neural network with more than one hidden layer. In such a case, it's called as a deep neural network. Okay, or if you have more than one hidden layer, it's called as deep neural network, or the entire problem can be called as deep learning model. Okay, although it's a very loose term to, it's a very loose definition of deep learning model, but still, it's still called as deep learning model because your neural network becomes a deep neural network. Okay. Okay, let's see what exactly happens in each of these neurons. Okay, let's do one thing. Let's take one of these neurons. Okay, let me just take the pen. Okay, let's just take one of these neurons and just zoom it in. Okay, so if you see, we have three features here. Like, let's call it as x1, feature x2, and let's say the third feature is called x3. Okay, and we have three weights. Let's call it as w0, w1, and W2. Okay, and if you just zoom this one neuron, you'll get something like this. Okay, this is your neuron, and these are your input values, and you also have weights associated with those values. Okay. Okay, in the previous image, I didn't draw something which is actually really important for the model. It's actually called as bias unit. Okay, so this is what happened. Okay, like just like how you have intercept in your linear regression, you have something called as a bias neuron in case of neural network, and the value of that bias unit is always 1. Okay, whereas these neurons will take input values, this bias neuron will always have the value as 1. Okay, and the weight associated with that will be, let's say, w0. Okay, so what happens in okay, in each of these neurons, two things happen, or two calculations happen. The first one is called as association, or it's also called as summation, and the next thing that happens is called as activation. Okay, so in association, what happens? We just calculate the weighted sum of all the features. Okay, in this case, let's say we have features x1, x2, and x3, right? So also this one, let's call it as x0, or x0 is always 1. Okay, so what happens here is 1 into w0 plus x1 into w1 plus x2 into w2 plus x3 into w3. Okay, basically weighted sum of your input values with the weight, and that sum is actually called as output of our summation function or association function. Okay, so let's simply call it as wixi, okay, which is, I'm just calling w as our weight matrix. Okay, these values, and xi as our input values. Okay, so what happens in association is just weighted sum of these. Okay, the input values multiplied by the weight values. Okay. uh, so the next thing that happens in neuron is called as activation. So before we actually talk about activation, we have to understand something called as activation function. Okay, basically what activation does is it tells you if a particular neuron needs to be activated or not. Okay, or in other words, should the neuron actually send out some information or not. Okay, that is your activation function. So one of the simplest activation functions that we have is called a sigmoid activation function. It is exactly same equation as our logistic regression. If you remember, the equation is 1 divided by 1 plus e power minus some value. Okay, what is this value? We are just passing the output of this association function here, and that is your activation output. Okay, so as I said, this is one of the activation functions, which is our sigmoid function. But apart from sigmoid function, you can also use other functions like tanh. You can use linear activation functions where none of these calculations will happen. Then you have step function. You can use a lot of different activation functions. Okay? One of the latest activation functions, which is extremely popular, is called as ReLU. Uh, Although sigmoid and tanh are good activation functions, but they also suffer from some of the problems. I won't be going into the details of that because it involves some kind of mathematical calculations. But the problem is called as vanishing gradient, because I will talk about that when we talk about how the network is trained. Okay, but in activation function, what we do is we take the output of association function and apply some kind of a mathematical function that brings the value into a certain range. Okay, if you use sigmoid activation function, it will bring the value in the range of 0 to 1. Okay, if the value is 0, that means your neuron is not activated. If it is 1, it is completely activated. Let's say if it is 0.5, it is like half activated. Okay, that is what your activation function does. Okay, so if you use instead of sigmoid function, if you use tanh, okay, or hyperbolic tangent, you can actually get the value in the range of -1 to +1. Okay, here also, like -1 means it is negatively activated, +1 is positively activated, and let's say if it is 0, it's like not activating. Okay, or the output does not really it does not actually send any information from that, or it's simply called as not activated. Okay, so whatever you get here from the activation is your output function, okay, or output value. Okay, so if you actually look at, okay, let me just erase everything. Okay, actually, if you look at the previous slide, each of these neurons, okay, this is also the same thing happens here, also same thing happens here, also same thing happens, and here also same thing happens. Okay, only thing that will be different between these four neurons will be the weights will be different for each of these neurons. Okay, as a result, the calculation will be different from for each of these neurons. Okay, that is the only difference. Otherwise, everything else remains the same. This will be x1, x2, x3. Only thing that happens here is this w0, w1, w2 will be different for this and this and this and this. Okay. If you actually closely look at this, when we have the activation function as sigmoid function, this entire thing is exactly similar to your logistic regression model, right? So let's, in the next slide, I'll show how exactly we can represent a logistic regression model in neural networks with just one single neuron. Okay, so so this is how you can actually represent your logistic regression model. Okay, you have one neuron in your input layer plus one bias in bias neuron, and let's call, instead of calling it as w0 w1, we'll call it as beta 0 and beta 1. Okay, it's exactly same. Okay, now this is your input layer, right? And in hidden layer, what happens, there are two steps, right? One is your association step and the other one is activation step. And in case of association, what happens, it is nothing but beta 0 into 1, which is your beta 0, plus beta 1 into x. So your association output will be this beta 0 plus beta 1 into x, right? So now your activation function that you have set is sigmoid function. So what happens here is you just have to apply this value to your sigmoid function, right? So which will be 1 divided by 1 plus e power minus uh, beta 0 plus beta 1x, right? If you actually look at this equation, this is exactly what we get in logistic regression, right? So if you actually think about it, logistic regression is a classification model, right? So what exactly it does, it comes up with a decision boundary to separate between two classes, right? So what I'm trying to say from this slide is each of your neurons in your neural network will actually act as a logistic regression unit. Okay, if you use sigmoid function, or even if you use other activation function, it does something similar to what a single logistic regression model does. Okay. Okay, so this is logistic regression when we have one single feature, right, which is our x, right? What happens if you have more than one feature? This is what happens, right? So you have your bias unit, you have multiple features, like let's say x1 all the way up to xk. So each of these weights, we'll call them as beta 0, beta 1 all the way up to beta k. So what happens here? It will be like your one beta 0 plus beta 1 x 1 all the way up to your beta k x k, right? And when you apply sorry, beta k xk, right? So when you apply this activation function on this, that is nothing but your logistic regression with multiple features, right? So okay, again just reiterating, so what exactly happens here is if you use a sigmoid function as your activation function, each of the neuron does exactly same job as a logistic regression model. Okay, so let me just go back to the first slide. Okay, now if you see this architecture here, what exactly happens is, let's say these are our features. Okay, based on the weights that we have here, this is one logistic regression model, this is another logistic regression model, this is another model, and this is another logistic regression model, right? So what hidden layer does is it learns individual logistic regression models from this data set. Okay, now what happens in the next layer? From hidden layer, the output is sorry, the information is flown from hidden layer to output layer, right? Where some more calculations happen. Basically what happens, based on these weights, okay, you have these connections here, right? Based on these weights, these logistic regression models will get combined together, and as a result your model will be able to extract extremely complicated patterns. Okay, so it's almost similar to saying, okay, we have 4 different logistic regression models, let's combine all of them, output of all of them, and see what happens, right? So that is exactly what happens in your neural network models. Okay, because of this, okay, this is just 4 neurons here, right? Imagine what happens if you have 10 neurons, right? So it will be like combining 10 different logistic regression models. Okay, and one more thing is, if you have, again, this is an example where we have shown only one hidden layer. Imagine what happens if you have more than one hidden layers, right? So it's like saying output of logistic regression is fed as input to other logistic regression models, where even more complicated patterns will be mined, and finally those models will be combined together to get what output that we want, right? So because of this complexity, because of this architecture, the neural networks are extremely popular, and they are able to capture like extremely complex patterns in your data set. Okay, as a result, some of the problems that you can't solve using your regular algorithms like logistic regression or svm or decision trees can be solved using neural network models. Okay, uh, so as I said, the only thing that is different between these individual logistic regression models is these weights, right? So what happens, based on these weights, the individual logistic regression will learn different patterns, and then they will get combined, right? So how do we decide what weights these neural network connections should get, right? So actually, in fact, these weights are the most important aspect of a neural network. Okay, that is the whole crux of your neural network models. Okay, so how do we actually decide what these weights should be, right? So that is actually this whole process is actually called as the neural network training. Okay, so initially whenever you create this architecture, okay, so how do you create this architecture? You start with your input layer. Okay, so input layers should have exactly same number of neurons as your input features. Okay, if you have 10 features, you need to have 10 neurons here plus one bias neuron. Okay, so that bias neuron is always there. Okay, so output layers will have those many number of neurons as your output classes. Okay, or in case of regression, it will be one single output neuron. Okay, uh, and hidden layer neurons, it's something that you have to play with. Okay, there is no clear cut answer as to like, okay, it has to be 5 neurons or 10 neurons or 20 neurons. Okay, there is nothing like that. This is actually called as hyperparameter of the model, which means there is not a single optimum value for this. Okay, based on your data set, based on your architecture, the number of neurons in hidden layers might differ, and that is something that you have to like get with the help of trial and error method. Okay. Okay, but how, as I said, weights are the most important things, right? How exactly do we get those optimum weights? Okay, so the first thing is, whenever you create this architecture, you start with some random weights for all these connections. Okay, there are different ways in which you can randomize this or initialize these weights. Okay, simplest one is like select a value between, let's say, -1 to +1. Okay, or there are different ways in which you can actually learn these parameters, or you can initialize these parameters. You can use different distributions to come up with these weight values also. Okay, once you get once you initialize these weights with some random values, then what you do is, what neural network does is, it does two things to actually learn those optimum weights. Okay, the first step is actually called as feed forward or forward propagation. Both terms can be used. Okay, in feed forward step, what happens, you take your input. Okay, let's say in this case x1 x2 x3 is fed. So in summation step, what happens, you calculate beta1 x1. Okay, in this case I've used beta1 beta2 beta3, but you can also use w0 w1 w2 w3. Okay, so in this case what happens, you just create a, or calculate the weighted sum of all these features with the weights. Okay, so beta0 plus beta1 x1 beta2 x2 beta3 x3 with some random weights, of course. Okay, so that is your output of summation. Then you apply this your activation function, which is in this case sigmoid. Okay, and you get your output, right? uh, but for these input units, or for these input values, you also know the actual output value, right? Because, okay, I am just showing a supervised algorithm here. Okay, so let's say for these values of input, you also know the output, right? So let's say the output that we are expecting is 1. Okay, with these random weights and with the actual weights of our features, let's say we calculate all these different things and we get the output as 0.6. Okay, so the output from our neural network is 0.6, but we were expecting the output as 1, and we can actually use this information to calculate the error, right? So in this case I've just shown the error for one single data point, but in actual case you might have hundreds of different data points, right? Your training set is, let's say, 100 data points. Okay, so you have to feed each of those input values or input rows with the exact same weights, random weights. Initially you have to calculate the output, and for each of the rows you'll get your error values, right? The actual output that you're expecting is 1, but you're getting 0.6, so the error in this case is 0.4. Similarly, let's say the second data point had you're expecting the value to be 0 point, or let's say 0, but you got your output as 0.1. So in this case the error is 0.1, right? So in after that, what you do is, once you feed all your input units or input rows, you calculate error for each of the data points, and then you combine them together. Okay, we can actually use your continuous or your regression error matrix only, something like MSE or your SSE value. You calculate your SSE or MSE value. Okay, and that will be your total error of the model. Okay, this is what happens in a feed forward step. Okay, you take your input values, feed through the neural network with whatever weights you have, and you get the output. You compare it with the, you get the output from your model, you compare it with the actual value that we were expecting, and you calculate the error. Okay, so this is what happens in feed forward. And then comes another step called as back propagation. Okay, in back propagation, what you do, you take the total error that we calculated in the previous step, and you actually do something called as you take this error, propagate it backwards, and adjust these weights. Okay, so since we are taking the error from last layer and propagating it backwards, the algorithm is called back propagation. It's nothing but your gradient descent. What it tries to do is, it takes this error value, it propagates it backwards, adjust the weights in such a way that your error value decreases. uh, Remember gradient descent in regression. So what we did was we adjusted the parameter values in such a way that the error decreases, right? So here also we do the exact same thing. We adjust these weights in such a way that the error decreases. Okay, so okay, just to summarize it, in back propagation what we do is we calculate the total error, we take the error propagated backwards and adjust the weights. Okay, in this case I've just shown one single layer, but what happens is let's say your neural network has multiple layers like this. This is your output layer, you calculate error here, you go back with that error, adjust the weights here, go back here, adjust the weights, let's wait here, go back, adjust the weights here, and so on. Okay, whatever number of connections you have, whatever number of layers you have to go to each layer, adjust the weights so that the error decreases. Okay, um, that is what happens in a back propagation step. Okay, so in forward propagation what we do is we take our entire data set, feed through the model, we take our entire data set, feed through the model, get the total error of our model, right? In back propagation we take that error that we calculated in the previous step, propagate it backwards and adjust the weights in such a way that the error decreases. Okay, so this entire step is actually called as an epoch. Okay, so one step of forward propagation and back propagation is called as one epoch. So in one epoch what happens, your data set is fed, way and error is calculated, error is propagated backwards, and weights are adjusted in such a way that the error decreases. Okay, so in one epoch what happens, your weights are adjusted in such a way that your error decreases. Okay, so your neural networks are actually trained with lot of number of epochs. So what happens, you start with some random weights, you do one epoch, you adjust the weights, you do second epoch, your weights are further adjusted, you keep doing this epochs multiple times, let's say hundreds of epochs. So finally when you run this forward propagation and back propagation through those many epochs, your weights will get optimized, and finally after sufficient number of epochs you might get optimum weights for your data set. Okay, so this is exactly what happens in a neural network training. And finally after you train your model, you should get optimized weights for your neural networks for your data set. And this final weights of your neural network might be completely different between two runs, because in each run what happens, the output or final optimized value of these weights depend a lot on how these weights were initialized. Okay, so we'll take some examples and see how exactly that works. So just to summarize the entire training process of a neural network, we can put it into the below steps. Okay, so whenever you have a problem that you want to solve using artificial neural network, first thing that you have to do is you have to initialize your artificial neural network architecture. So this involves coming up with the appropriate number of layers, also coming up with the appropriate number of neurons in each of the layers. Um, so if your data set has 10 features, your input layer should have 10 neurons plus one biased neuron. So all these things need to be taken care of, and based on that you have to come up with your artificial neural network architecture. Okay, also one more thing is you have to decide like if you have to come up with a single hidden layer neural network, or a multi hidden layer neural network. Okay, so all these things are done in the first step, where you initialize your ANN architecture. And once that is done, and second thing is, I think I didn't tell you this earlier, but if you actually see every single calculation that happens in neural network, everything has to be in numerical values, right? You can't use categorical values in your artificial neural networks. So if you have a categorical feature, you have to convert those categorical features into a numerical value. Okay, and also even if your output is categorical, even if it is classification, you have to convert it into some kind of a numerical value. Okay, because everything happens based on numerical values here, so everything needs to be converted to numerical values. Okay, so that will be your second step. And the third step is, once you initialize your ANN architecture, you have to provide some random weights to the network. So each of the connections in your neural network is randomized, or you give some random value. As I said, there are different ways in which you can randomize your or initialize your weights. Okay, you can initialize it with some values between 0 to 1, or you can initialize it with some normal values. You can do a lot of different normal you can do a lot of different initializations for your neural network. Okay. Once you do that, you have to set up your activation and association function. So most of the cases, association functions will not change much. I mean, it will be simply your weighted sum of your weights and input values. But activation function is something that you might have to change. Okay. As I said, sigmoid and tanh are good, but they're pretty old and they suffer from some of the problems. One problem is vanishing gradient problem. What it means is, in case of back propagation, right? So whenever you take your error and propagate it backwards and adjust the weights, okay, if your neural network is deep, as you go towards the last layer of your neural network, the weight adjustment happens at a very, very tiny fraction, because it uses something called as a chain rule to calculate this weight gradients. Okay, so which is nothing but the weight adjustments here will depend on the previous weights, and previous weights will adjust on the previous layers, and so on. Okay, so as a result, what happens as you move towards the last layer, or when you move the when you propagate your error backwards in this direction, as you move towards layers, your gradient that you have to use for adjusting your weights will become smaller and smaller. Okay, this is called as vanishing gradient, and this is a big problem in case of your sigmoid and your hyperbolic tangent activation functions. Okay, so that is why, but that is a small problem. Like we have some activation functions like ReLU, PreLU, leaky ReLU. A lot of different things are there, which are like latest ones. So if you use those activation functions instead of sigmoid or tanh, you will get rid of this gradient vanishing gradient problem. Okay, so once you have set up your association and activation function, the next step would be to start training your model. And for that, what you have to do is take your entire data set, push it through the model, get your total error for the model, take that is your feed forward step or forward propagation step. Then take that, that is your step 5. Okay, step 6 would be like you take that error from the output, or your entire data set, take that error from the last layer and propagate it backwards and adjust the weights in such a way that use some optimizer. uh, it's simply your gradient descent optimizer. Use gradient descent to adjust the weights in such a way that your error keeps decreasing. So you, the step 5 and step 6 are called as one epoch. Okay, and you have to keep doing this again and again until you reach the weights which are optimum for your data set. Okay, so you'll stop when your error has hit the lowest value. After a certain number of epochs, you might end up with a neural network with a certain error value, and if that error value is satisfying, you just stop it there. Or sometimes you will not get that, you have to stop it after a certain number of epochs. Okay, it all depends on your use case, your values. So if you want neural network with really, really low error, if it is possible, then you have to train it for more number of epochs. Okay, but at certain point it might not decrease further, so that is where you have to stop. Okay, so this is how your neural networks are trained. Okay, so these steps are exactly same for all your artificial neural network trainings, and these will be almost similar for even your deep learning models. Okay, so as I said earlier, the activation functions that I showed was only sigmoid function, but apart from sigmoid function, you can use a lot of different variants. Okay, you can use all these functions here. This is slightly old. Okay, but apart from this, you can also use relu, prelude, leaky relu. A lot of different activation functions are there. Okay, basically what activation function does is takes your input, okay, output of your summation method, and it just converts it into a range. Okay, so if it is smaller value, yeah, that means your neuron is not activated. If it is higher value, it means it is activated. Okay, that is the whole point of activation functions. And if you use these functions, you might end up with the uh, vanishing gradient problem, whereas ReLU, leaky ReLU, all these things does not have that problem at all. Okay. Um, okay. Then finally, okay, a little bit about the pros and cons of artificial neural networks. Okay, so artificial neural network is extremely powerful model. Okay, so when this is used when your data set is huge. Okay, when as I said, artificial neural network requires a lot of data points to train. Okay, if you have a lot of data points, the model will learn pretty nicely. Okay, so it's one of the algorithm that you should go for if your data set is huge and you have a lot of features. Okay, okay, when I said huge, I don't mean number of rows. Okay, okay, if it is number of rows, then you can also go for other algorithms like random forest or decision trees or other algorithms like boosting or other algorithms. But when you have a when you have a problem where you have a lot of features, then it is better to go for artificial neural networks. Okay, and as I said, these individual neurons act as logistic regression models, and they get combined together in the last layer. So as a result, the algorithm will be able to come with extremely complicated problem, extremely complicated patterns. Okay, even with just one single hidden layer, it is able to come up with complex decision boundary by combining output of these individual logistic regression models. Okay, just imagine what happens if you have more than one hidden layers. The learned pattern would be even more complicated, and as a result, this is the whole power of artificial neural networks. Because of this concept, it's able to come up with extremely complex, or it can be used to solve extremely complex problems. Okay, sometimes artificial neural networks are can solve some problems which can't be solved by other algorithms. Okay, for example, these image problems and all, you can't use your regular algorithms. That is where you have to go for these artificial neural network algorithms only. Okay, uh, okay, the last pro is that with more than one hidden layer, it becomes a deep neural network, and as a result, the problem is called as deep learning. It's a very loose definition. Actual deep learning models will have some other architectures, but yeah, even these are called deep learning models because you are using deep neural networks. But with some more additions or some more modifications to your deep neural networks, you will be able to solve extremely complex problems like self-driving cars, your image classifications, your speech recognition. All these problems can be solved using artificial neural networks. Okay, actually, in fact, only artificial neural networks can be used to solve these kind of problems. Okay, but these are some of the positives of the algorithms, but at the same time there are some limitations also. First thing is, okay, by the way, why is this layer called hidden? Because it is hidden from the end user. Okay, you will be able to see what values go into the input layer, what values you get from output layer, but these are like you can't really intuitively make sense of these values that are in hidden layer, and that is why the entire layer is called as hidden layer. Okay, so that is why neural network models are also called as black box models. Okay, because if you put your inside input values, you will get your output values, but exactly how it works, nobody will be able to say. Okay, uh, and that is one thing. Second thing is, neural networks are extremely complex algorithms. So if your problem is simple, don't go for artificial neural networks. Okay, so artificial neural networks should always be your second option which means if you can solve your problem using any one of the simpler algorithms like SVM or logistic regression or random forest or any other algorithm, go for that. If you're not able to solve it using those algorithms, you're not able to get good prediction scores, then only it is advisable to come for artificial neural networks. Okay, because just because it is extremely complicated and it takes a lot of resources to train your model. Okay, that is our next limitation. The model building takes a lot of time and it's computationally expensive. Okay, uh, even a fairly simple problem needs a lot of time to train, and as a result, as I said, this will be your second option to go for. Okay, and one more thing is, since the model training takes a lot of time, this parameter tweaking might take a lot of effort. Okay, for example, how many neurons should be there in hidden layer, or what kind of weight initialization should I go for? Okay, all these are parameters of the model, and that would require tweaking, and that becomes difficult because this entire process is a little complicated. Okay, but there is one more pro that I missed to mention here. That is, in case of artificial neural network, let's say you had 1000 rows data points, okay, and you have trained your model, and your weights are learned or trained. Okay, you get your final model with the weights, right? So now let's say in the new let's say today you get some more data points, let's say 100 more data points. Okay, and you want to train your model with all the 1100 data points. You don't have to start from the very beginning, you can just start from where you left off in the last time. So you can take your already trained neural networks. Okay, instead of randomly initializing these weights, you start with the weights that you learned from the previous step. Okay, and you start from there, and from there you start your training process. You do feed forward and back propagation and adjust the weights. Even then, even with the new data points, you will be able to learn the new weights from that point itself. Okay, so so it's not possible in any other model. For example, random forest, once you build your model, you can't go back and change the model with new data points, right? But in artificial neural networks you can do that. And as a result, whenever your data comes in at regular intervals and you have to keep upgrading your model, neural networks are really good. Okay, because you, without changing a lot of things, you can actually train your model from where you left off at the last step. Okay, so these are some of the pros and cons. Okay, let's also look at a demo app. Okay, it's a app that was developed by some scientist to demonstrate how exactly neural networks work. Okay, I'm just sharing that. Okay, let me just go ahead and share that. Okay, yeah, so this is the application that I'm using. Okay, it's called backpropagation. Let me just tell you what exactly this does. Okay, this is a demo application that Dr. Syed had built. Okay, just to demonstrate how a neural network training happens. Okay, so you have your first feature here, second feature here, and a bias unit for your input layer. So this entire thing will be your input layer. Then this is your first hidden layer, this is your second hidden layer, and this is your bias unit for this layer. Okay, now if you see, there is a reset button. This is nothing but your model initialization. We'll talk about that. This iterations is nothing but your epochs. Okay, and then there is something called as run data. We'll talk about that. But before that, summation and activation is your summation is nothing but our association function, and activation function is in this case it is your sigmoid function. Okay, so what happens in summation is, let's say in this case, okay, w1, in this case w11 into value of this plus w21 into value of this plus w31 into value of this will be your output of sum one, and that gets activation, that output of this function will be fed as input to the activation function. In this case it is sigmoid. Unfortunately in this case we can only use sigmoid. If it was something else we could have seen how the values changes, but in this case since it is demo, it has only sigmoid function. Okay, so that will be your output from this, and this will be your output of this neuron. Okay, so for this, what happens, y1 into w13 plus y2 into w23 will be plus bias unit into w33 will be your input to this summation function here. Okay, and again from this you calculate your sigmoid function or this logistic function, and the output will be your output. Okay, so since this is a demo neural network, we'll be using a very small data set. Okay, in this case, what we will do is we'll use OR gate, and we'll see how the model learns the pattern associated with OR data. Okay, so if you actually see, it takes three values here. Okay, it takes x1, x2, and target. Okay, so x1 and x2 is your feature, and the last value will be your target. Okay, so let's see, let's create our data. Okay, 0 0, if your input is 0 and 0, the output should be 0. So if it is 0 and 1, sorry, 0 and 1, your output is 1. Okay, if it is 1 and 0, again your output is 1. If it is 1 and 1, your output is also 1, right? So how exactly it works? Okay, let me just do one thing. Let me just click on this reset button. Just or initialized. Okay, so just let me just go ahead and click this reset button. If you see, it got some random initialization values. If I just click on reset again, it changes. So if you see, I'm just clicking this reset button multiple times and see how the values are changing. Okay, now let's take one of our data sets. Okay, like 0, okay, and 0, and for that we are expecting output of 0, right? So if I just click on forward propagate, what happens? It takes all these values, pushes it through this model, and gets you the output here. Okay, just let me just click on this forward propagate. Now, if you see, with these weights, the output that I'm getting for 0 0 is 0.52209. Okay, you can just see that. Okay, here in this case, the summation value will be 0 into this 0 plus 0 into this again 0, 1 into this, that is your output here. Okay, or output of summation function here. Okay, when you feed this value to in this function, 1 divided by 1 plus e power minus of this, you get an output of 0.33. Okay, similarly here you get since this weight, the last weight is 0.97813, only that you'll get, because the output is input is 0 0, and if you feed that to this function, your output will be 0.72674. Okay, now once you have this in this neuron, what happens? 0.33179 into 0.51739 plus 0.72674 into minus of 0.37 plus 1 into 0.19229. Okay, and the output is 0.08840. Okay, that is the summation output for this neuron, and when you apply your sigmoid activation function, you get an output of 0.52209. Okay, but you are expecting the target to be 0. Okay, so our error is around 0.48, right, or 478, right? So if I just click on back propagate, just look at how these weights will get adjusted. For example, if you see this weight, right now it is 0.51739. If I just click on back propagate, this one will change from 0.517 to something else. Okay, see, it got adjusted by a small value, because what happens, it took this error, it uses this error calculation. Let's not go into the mathematical detail. You will get a lot of YouTube videos to actually understand how exactly this error calculation happens. But if you just take this error value and propagate it backwards, you see that each weight in our neural network got adjusted. Okay, in this case I'm just showing it for one data point, but actual case, what happens, instead of just one data point, every single data point will be sent through the network. Okay, so let's just do back propagate. Okay, we already did that. Now with these adjusted weights, if I do forward propagate, earlier the output was 0.522. Now if you see, the output is 0.495, right? Because it tries to match the output with the target as 0, which means the error is decreasing, right? So if I just keep on doing this, you'll see that the weight will get adjusted and this output will become closer to value of 0. Okay, so this is how neural network is trained. Okay, anyway, let's not do it one by one. Okay, let me just reset this again. So now what happens, this entire network got like reset, initialized. Okay, now let me just do iteration 1. Okay, what happens is this is nothing but your epochs. Okay, if you set it as 1, it will run one epoch. Okay, which means one forward propagate and one back propagate step. Okay, so let's see, in this case, if I do iteration, it will take all the data points instead of taking one single row. Okay, now, if you see, there is some error also of the model. For all these data points, the MSE is mean squared error of the data set or the model is 0.475. Okay, so one iteration is not enough. So let me just do some 1,000 iterations. Okay, let me just reset 1,000 iterations and I'll just run the data. We'll see what happens. Okay, before we do anything, we'll just reset. We'll just see what happens if we feed 0 and 0. Okay, see 0 and 0, we are expecting the output to be 0, but the output is 0.67, right? So 0 and 1, the output is 0.65, but we are expecting the value of 1. Okay, 1 and 0, we are expecting a value of 1, but output is 0.65. And when it is 1 and 1, the output is 0.63, but we are expecting 1. Okay, so let's do this 1,000 iterations. We'll see how the weights get adjusted so that the error decreases. Okay, let me just click on this run data. If you see this here, the error keeps decreasing. Okay, it keeps decreasing, which means the model is becoming less and less error. Okay, or a model has less error in each of the epochs. So after 1,000 epochs, our model error has reduced to 0. Let's see, let's just wait for 1,000 epochs to finish. 0.228. Okay, but if you see, the error is still decreasing, right? So probably 1,000 epochs is not enough. We may have to run it for another 1,000 epochs. But now let's see in between what happens if you feed 0 0. Okay, earlier it was giving us something around 0.65. Now if you feed 0 and 0, the output is 0.06. Okay, which is very close to 0. Okay, if you feed 0 and 1, with these calculations, the output will be 0.95, which is very close to 1. Okay, if you feed 1 and 0 to the network, you see again the value is around 1, which is what we were targeting, right? And if you feed 1 and 1, the output is around 0.99, which is again very close to what we were expecting. Okay, so let me just go ahead and run another 1,000 epochs. Now if you see, suddenly the error has decreased because the model has learned something. Okay, it's really good now. So after like 1,000 plus 1,000, 2,000 epochs, the model has learned really it has really trained well. So your error has been decreased from 0.5 to 0.034. Okay, which means it's pretty good error. And with that error, we will see how exactly the output looks like. Okay, let's see 0 and 0. If you feed your 0 0 with these updated weights, the output is 0.03, which is very close to the expected value, which is 0. Okay, if you feed 0 and 1, you expect the target to be 1, and if you see, it's around 0.975. It's very close. Okay, so 1 and 1, you're getting around 0.994. Okay, so this is how it works. Again, as I said, this is just a demonstration app. Okay, that is why we just have these two features. Instead of these features, you can actually feed some other function that you think is good. Okay, we can actually do that also. But only thing is, since we are using output as sigmoid, or we are using sigmoid activation function, the output has to be between 0 and 0 to 1, because if you see, the final value whatever we get here is fed to your activation function, which is sigmoid, and the output is always between 0 to 1. So even if you feed your data set, try to make sure your target is between 0 to 1. Okay, but this is how your neural network model gets trained, and this is how your entire artificial neural networks are trained. So finally, to talk about deep learning models, as I said, deep learning is not just a neural network with more than one hidden layer. Uh, that's a very loose definition, but there is something called as deep learning architectures. There are various different architectures that people use. Okay, well, some of the popular ones are like convolution neural networks, which are mainly designed for computer vision problems can be solved using convolution neural networks. For example, it's one of the technique that you use very much in your self-driving car, because what it has to do is it has to identify different objects on the road, okay, using your head-mounted 3D camera, right? So for that we use this convolution neural networks. Okay, basically what these deep learning architectures do is they actually have some more layers before your regular ANNs for extracting your features. Okay, in case of images, we have this convolution operations that extracts features from the images. Similarly, we have something called as recurrent neural networks, which can actually capture some kind of sequences. For example, text, right? Your words that you write has some kind of a sequence, right? So recurrent neural networks will be able to capture that. And finally, what happens, everything will be processed in some of the layers before your ANN. Finally, your ANN will be fed with the output of these different layers. Okay. Similarly, there is something called as GANs. Okay, before that, convolution neural networks are mainly for images. Okay, recurrent neural networks are mainly for sequences. For example, text, or people are using RNNs or LSTMs. Okay, LSTM is long short term memory. They're using this for even creating music or video processing, a lot of different things. Okay, wherever you have a sequence, you can actually use RNN or LSTM. Okay, even for that matter, how does Google know? How does Google autocomplete your search terms? It uses some kind of LSTM model. Okay. Finally, the latest technology or latest algorithm in deep learning is called as GANs. Okay. So what they do is you can actually come up with new data points. For example, if you see this face here, this looks like a celebrity face, right? But what if I tell you this person does not exist? This is actually a computer generated face using an algorithm called as GAN. Okay, so these are there are a lot of different use cases of deep learning, starting from robotics to IoTs to image processing problems to the GAN problems where you're trying to generate new data points. Deep learning is used everywhere. Okay. Uh, so this is a very basic introduction to machine learning. In the last 5 days sessions, we talked about what different algorithms are there in machine learning, how exactly a regression algorithm works, how exactly a classification algorithm works. And today we saw how an artificial neural network works. And finally, very basic introduction to deep learning. Okay. Thank you, everyone. We'll have some probably question and answer sessions.
Thank you for your valuable time and informative session, sir. We have reached the end of the faculty development program on machine learning. In this regard, I would like to take this opportunity to thank the VVCE management and our beloved principal, Dr. B. Sadashiva Gowda, for their support and encouragement. I would also like to thank Dr. A.B. Rajendra, HOD, Department of Information Science and Engineering, VVCE, all the faculty coordinators, and all the participants for making this event a grand success. Thank you, one and all.